first. Sharing the screen here. Let's get an intuitive look at the backward difference, center difference, and forward difference. Just take a look at the picture here. Here. Okay, this picture explains a lot of things. You already got the backward difference formula, center difference formula, and I just list out the backward difference formula here because the forward difference formula is quite symmetric way, and then you can draw the pictures in another way. So let's see, what's the slope of a function? The slope of the function, if you take a look at the big picture here, the blue line is the f function. The blue line here is the f function. Okay, good. And what's the slope of the function? What is the derivative? The derivative is just a tangent line at that point. So this is how x0, and then the tangent line, it looks like this. And then the tangent line, so x0 is this one, and then the tangent line, it looks like this. Okay, good. And what's the backward difference formula? The backward difference formula, if you take a look at the backward difference formula, this is the backward difference formula. It's actually, okay, what's happening here? And you take the functions evaluate at x0 plus h, and then you take the f evaluate at x0, and then connect them with a line. And then the slope of this line is just the backward difference formula, the value. So for the center difference, we have different things, but it's connecting two different points. And for the center difference here, we are connecting the x0 plus h, the functions at the point at the x value where the x value is x0 plus h. And then there's another point, and then that is the point on this curve, the function f, and evaluated at the x0 minus h point. And then we connect them with a line, and then the slope of this line, and then that's the value we get from the center difference formula. So you could see we are going to use the slope of this line to approximate this tangent line, the slope of the tangent line. And here we are going to use another line to approximate the slope of the tangent line, the slope of tangent line here. So this is the intuitive look for this finite difference formula. So I'm going to give you some conclusions here before we move to the next. But could you tell me from the picture that which one you prefer to use? Which one is a better approximations, do you think? You think which one is better? The center one, right? It's more parallel to the slope of the tangent. And do we get some conclusions from the theoretical derivations here? We have already derived something about the center difference of finite backward difference before. So let's see. I'm going to do some conclusions here. Let's see. Actually, the backward difference formulas is quite symmetric to the forward difference formula. So I'm going to skip the forward one here. And so let's see the forward difference formula, the backward one, and then the error looks like this. The error term, bigger, okay. The error term here is the 1/2 and then f prime k0 and then h. And the error term for the center difference formula is, let's see, we have the -1/6 and then f the third derivative k0 h squared. If you look at the scale here, this is with the h order 1, and then this is h order to the order 2. So the h is a pretty small value, and then if you have the higher degree here, and then which means that the error can be smaller. And that's why we have better approximations in these pictures for the center difference format. Any questions? So this class, I will also introduce another way to approximate the derivative. and then with a higher order, which means that we have more accuracy there. Any questions? No. And how these pictures can help you understand the whole things here. Next, let me see. The next things we have to talk about the rounding off errors. So we just mentioned the rounding errors in the rounding errors for the number, for the operation, additions, divisions, and multiplication. And let's see if we count this into the count the rounding off errors into the finite difference formula, and then what do we have? So let's say we have some rounding for the value here, and then some rounding for this value. And then if we count the rounding of errors into our calculation, and then what is the error? What is the total error looks like? That's the whole thing. So let's just look into the standard difference formula, and then to see the total error for the calculation if we count the rounding of errors into the total error. So for this standard difference formula, and then now you have the total error should include two parts, right? One part, if we count the rounding off errors into it, and then the total error should come with, so the total error in approximations of the f prime x0. It has two parts. And then the first part is coming from the finite difference formula. And that's this part. So this is the error term from the finite difference formula. And that is one part. So this one part is the error from the finite difference formula. And the other part is coming from the rounding off error, if we take the rounding off errors into account. Any questions before we move to the detailed calculation? So here, if we use this standard difference formula and in the computer, if we do some rounding off for this number, we some rounding off this number. Let's say the division is accurate. And then the total error in the approximations of the derivative, it has two parts error. And then the error one, the part one should be the error from the finite difference formula. And then the second part is the rounding off error. And let's calculate all the things. And then you will see we should make a trade-off here to choose the step size. So if you just look at this one, right? If you just look at the errors from the formula, and then you will see, oh, let us just keep decreasing the step size h. And then we would get a more accurate result. But the things happens not in this way. Does not happen in this way because you will see this. We need to do a trade-off here for the h size, the size of the h. So the following things is not as interesting as what I just said because you need to do some computation. Now let's do the computation. Wow, that's the whole page. Don't worry, I will do it one step by step. Don't worry. Let's do this. So first of all, as I mentioned, let's say we have some rounding off errors for the terms. The first one and the second one, they're in the numerator. And so this is the center difference formula. And then let's say we have, but in the computer, we have some rounding off here. In the computer, it has rounding off for the item x0 plus h and the fx0 minus h. And let's denote this rounding off value as we just mentioned this in the previous class. In the chapter 5, we can use the delta to represent the rounding off value. And 1 plus delta plus, and then minus fx0 minus h, and then 1 plus delta negative, and divided by 2h. So here we have the delta plus and delta negative here. And what does it mean? Where the delta plus and delta negative are the relative error for the rounding off f0 plus h and the fx0 minus h. And delta plus and delta negative is just smaller than the epsilon. And then the epsilon, we also mentioned this in the chapter 5, and this is the machine positions here. If you remember what we did in the chapter 5, I just mentioned this in case you forgot this. And then I have mentioned this in the chapter 5, the rounding x equals to x and then times 1 plus delta, and then the delta is the relative error. Do you remember this? And then, but now I just changed this to fx0 plus h, fx0 plus h, and then this fx0 plus h. But here I have two numbers, so I did know this rounding off errors for two different sides, and then this is the plus side, and which means that this is the rounding off error for this term, and then I use the negative sign here, the subscript here, and then to denote this is the rounding off error for this number. Any questions before we move to the next step? Okay.
They could be different values, right? It's not just
It could be different value. Because it's rounding for different numbers, and then we could have different errors. But because this is the rounding off in the computer, and then it should be less than the machine positions.
Is it typical that like delta plus is always positive?
No, it's just like a notations to denote this is for the x0 plus h, the error. So it could be negative, it could be positive. Because it's rounding off, it could rounding down, or it could rounding up.
Oh, yeah.
Good question. This is just all the notation, and then we are going to get the total error. Let's analyze the rounding off error. Let's see. So the rounding off error, it should look like this. fx0 plus h, and then this is the number we are going to use to calculate the finite difference formula, and we are going to use some rounding off number here, and then we use the these notations to denote this is the rounding off the number. The numbers we use after the rounding. The number we use after the rounding. And we want to calculate the relative error here, which means that we want to write it into this format. And So here we are going to write it into x0 and then plus h and minus fx0 and then minus h and then divided to h. And then what is the error? The error should be the error. I'm going to write the error here, RH. And how do you calculate this number? And then you just need to explain this explain this expressions, and then this one times one, and then subtract this one times one, and then that is just this part. And then for the error term, and then that is this part times this part, and then minus this part times the delta negative side here. So the RH is equals to RH equals to fx0 plus h, and then delta plus, and then minus fx0 minus h, and then delta negative, and 2h. And this is the error. This is the approximation number for that finite difference formula, and then this is the actual, the true real number, real value for the finite difference formula, and then this is the error. And the error term, you will see the error is coming from the rounding off for this time, and then the rounding off for this time, and then do the subtraction and divided by the 2h. H is the step size. And let's do a BAM, get a BAM for this error term. So this error term, I use the RH to denote it. And then now let's get the BAM for this rounding off error. So I'm going to get the absolute value size for that RH. And it's bounded by the absolute values of the first term and plus the absolute value of the second term. And this is the BAM for the absolute value. And let's see, what do we have here? And don't forget that we have the rounding off error is smaller than the machine positions. So let's get the BAM for this and then for this. And then they are both smaller than the epsilon here. So at the end, I got this fx0 plus h, and then plus the fx0 minus h, and then I should get the absolute sign here, absolute value sign here, and divided by 2h, and then because the delta a plus and then delta minus sign, the absolute value of this area here could be bounded by the epsilon, and then so I have the epsilon here, and now I could say, what I'm going to say is that because the h, it could be very small, right? And I'm going to use approximately equals to this one. And so I'm going to replace the fx0 plus h, fx0 minus h with 2fx0 because it's close numbers to the fx0. So here I'm going to replace this with the 2fx0. It's not equal. This is just approximately equal to this number because the h is pretty small here. And then we assume that this function is continuous, and then the change is not so much. It would not just drop down. So it could be continuous. And then if it is continuous and then the change is not so much, and I can use the fx0 to approximate the fx0 plus h, and then fx0 minus h. And because this one, I just assume that this is continuous, so I can use these two numbers to this number to approximate these two numbers here.
Approximating that to fx0, wouldn't the twos cancel out from the bottom and then the top?
From the bottom to the top?
Yeah, the denominator of 2h, but then you approximate it as 2fx.
Oh, this one, the 2h. Yeah. I forgot the 2h here. Do you mean this?
Yeah, but then they cancel out, right?
Yeah, I can cancel it out. And then that is fx0 epsilon divided by h. Do you
Yeah.
mean this? Okay. There's some typo just now. This is the return from the rounding off. But now let's go back to what we have here. We are going to get the total error. Total error, and then we already got the rounding off error, and then we also want to count the errors from the finite difference formula. So the next page we are going to get the total error. This page should not be here. And so the total error, we are going to get the total error. And I'm going to use this is the total error. And then I'm going to use the subscript T to represent this is the total error. And the total error is just the actual, the true derivative, and then subtract the computer calculation. The computer is using the rounding off value. So I have f0 minus h, and then the rounding off value here. And how can we estimate this value, this error? And you will see I'm going to add some time into this expression and then subtract the same items from these expressions. So here I'm going to do this. Subtract the original formula, that is the true value of the finite difference. And then I will add this back to the expressions here. So I with the add something and then subtract the same thing, I'm not changing the value of the expressions, right? And so the next, I'm going to take the absolute value and then doing the inequality here. And this, taking this absolute value, and then it gives me the smaller than or equals to. Here I got this. So because this is the so this is because the a plus b absolute value is smaller than the a absolute value, and then plus the b absolute value. So I divide this into two parts, and plus this. And doing the subtractions here. The size is too big. The size is too big. It's just too big. Okay, good. And subtract the later item here, the last item here. So you would see this is the way we got the results, the total errors. And then this is what we just mentioned at the very beginning. The total errors contains two parts. And then you will see this part, this is the actual, this is the derivative of that. And this is the finite difference formula. And this part, what is this? This is the error from the approximations, the finite difference formula. And what's this part? We have the actual finite difference formula here. And then this one, we have some rounding here. So this one is just a rounding error. So that is what we just mentioned a few minutes ago. We write the sentence there, write out the words there. And then this is how we get to the this two parts of the error here from the mathematics way. And so the first part is just the, and we have another way to call the errors from the center difference approximations. We can call it truncation error. And so this is the first part is the truncation error for the center difference formula. And the second part is just the rounding off error, the round off error. And let's go back to take a look at the notes here. So from the center difference formula, we got f prime f x 0. This is f prime x 0 minus the center difference formula, and then this is our truncation error. So I'm going to copy this to the to here, and then I got this. So this is from the previous class, and I got the absolute value of the truncation error, and then the C0 should be between the x0 minus h and the x0 plus h. And the second part is the rounding off error, and then we get this from here. So I'm just copying then this part to the analysis here, and then I got fx0 because I'm going to take the absolute value. So I have this epsilon divided by h. And now I'm going to take one more sign here, take one more inequality sign here, and then this one is more than or equals to 1/6, and then taking the infinity norm of this value, infinity norm, and then h squared plus fx0, and then absolute value sign epsilon h. And in case that you don't know the definition of the infinity norm, and then so the infinity norm, where the infinity norm here, so we have the third derivative here, right? It should be the function and then infinity norm. In case that you don't know the definitions of the infinity norm, and then it's just define it, it's a norm of a function, and it's a norm defined as the infinity, that is the maximums. There is not so much space here. It's just the maximums on the interval. And then, but we are going to consider the intervals x0 minus h and x0 plus h. So the infinity norm here is defined as the x in between the x0 minus h, x0 plus h, and then taking the absolute values of the functions. Absolute value of the functions here. So hence, here we have the third derivative, and then taking the infinity norm, and then which means that we are going to take the maximum of the third derivative here, and then on the interval x0 minus h and x0 plus h. Why do we have such an interval? Because the c here, it should be inside this interval. And I'm going to use the maximum number on this interval to bound the number here. Does that make sense? So C0 could be anything in between this interval. So I'm going to use the maximums on this interval to bound this number. Any question here? So this is the definitions of the infinity norm, but the infinity norm is just the maximum of the number. Maximum of the functions on this interval. So do you see some things happening here? You will see if for the truncation error, this is truncation error. If we let the size of the h go smaller and smaller, and then this part of the error would become smaller and smaller, right? But for the one of error, and then that is the total different case. So as long as the machine precision, and then it's just a fixed number, and then fx0 is also a fixed number, right? But if you keep the edge, let the edge go smaller and smaller, and then the run of error is going bigger and bigger. So what is the best edge? And then how can we decide the best edge here? Yeah, pick the derivative, and then that to be the critical point. Yes, that's a clever way to do it. So we are going to do it this way. So let's say this everton is the function of h. So now we treat this everton. So this is a fixed number, this is a fixed number. If we are going to take a look at the x0 here, the derivative at the x0, and then this number is fixed, this number is fixed, this number is fixed, and then this is just a function of h. So the total error, we view the function, we view the total error as a function of h. The total error et as a function of h. And then the et, and then this is a function of h. And then we want to minimize such an function, and then which means that we want to minimize such a total error here. And we want to minimize this. We want to minimize this error term. And if we want to minimize this error term, and then from the calculus class, and then we need to get to the critical points. And so the things we need to do is to get the derivative of the total error function, and then this is the derivative, and then but it's about the h, and then we want to let it to be 0, and then we get I'm not going to do the detailed calculations here, but if we solve these equations, and then we get the uttermost edge. And you can double check the second derivative here. The second derivative should be positive. And then that's which means that this is a minimum point. I just get the critical value, and then but you can double check the second derivative, because it could be critical point, could be maximum number, it could be minimum number. But when the let's see, the minimum point, and then the second derivative is should be positive, right? Let me see, the second derivative, this is negative and this is positive. Yeah. The second derivative should be positive, and then you can double check the value there. Okay, but I just simplify my calculations here, and then but you need to check the you also need to check the derivative of the second derivative at this point. It should be so the second derivative here, it should be positive, and then so we have this. We can conclude that this is the minimum point of the ETH. Hence, the H star achieves the minimum value of the total error. Here. And if you substitute these things back to here, into the total value, total error value, and then you will see the total error is just in the order in the magnitude of the epsilon, this is the machine error, and then let me see, it's just the 2/3 of the machine errors, and then it should be in this magnitude. Any questions here? If you substitute the optimal value back to here, then we get a number. This means that a constant times this number. Any questions here? The big O is a notation for constant and then times this. It's approximately this.
The two and 2/3.
What's 2/3?
Epsilon's raised to 2/3.
Yeah, it's 2/3.
Where do you get that?
So you just substitute this back to here. So you treat this one as a constant, right? And then you have epsilon 1/3, right? And then you plug in back to here, and then you get epsilon 2/3. And then this one, epsilon divided by epsilon 1/3, and then you also get epsilon 2/3. This makes sense. I'm just plotting. I skip the details here, and then I just tell you plotting. Okay. But here now you know that is just the calculations. Plotting back to here. Epsilon 1/3, and then plot in here, and epsilon 2/3. Epsilon 2/3. Questions? Yeah. Question before we move to the examples to see and examples of this optimal H here. A concrete numerical examples for the optimal H. So let's see. This is just something from the previous classes. I'm going to delete the page here. No, just keep here. Just keep here. Okay, good. So one more thing from the previous class notes. So this means that we don't get machine precisions for the finite difference for calculations in the computer. We have the rounding off for the numbers, rounding off for the number, and then it's inside the machine's precisions. But when you apply the finite difference formula to approximate the derivative, and then this is just the errors for the derivative terms, and then we cannot achieve the machine precisions. If this is machine precision, and then this order here, it should be 1. But here we have only the machine precisions and the 2/3. And then why does this matters? It means that if we use the finite difference formula to approximate the derivative, and then we cannot get to the machine precisions, and then which is not as good as the machine precisions. And let me see, do we have one more chart here? Got it. So the machine precision, so let's say is 10 to the -6. And then now if you use finite difference formula, and then some rounding of the value there, and then to approximate the derivative, and then what is the error time? The error time is 10 to the -6, and then 2/3. And then which means that the errors could be 10 to the -4. And so the rounding of errors for just a number, and then it's 10 to the -6. But if you use the finite difference formula to approximate that derivative in the computer, and then it's 10 -4. So this error is bigger than the machine precisions here. Does it make sense? So I have exclamations mark here because we cannot get as precise as the machine precisions. That's why the 2/3. So let's see. We have one concrete example here. We are going to approximate the derivative here, and then this derivative is the 0.9. The cosine function. Let's see. Consider. What's the function here? The function is sine. The function is should be the sine function, and then we are going to calculate the derivative at the 0.9. And if you go to use some computers programming or the Wolfram on online Wolfram and then calculate the cosine 0.9, and that is the derivative of the sine evaluated at 0.9, and then this is the true solution, the true value. And but if we use the formula, the approximation formula, this is the center difference formula. It's a good one. It's already a good one. And we are going to use the formula to approximate that derivative here. And then let's take a look at the table. And then we are going to use different values of h to approximate this value, approximate this derivative. And let's see, in this table is the results we get. So we are going to use this standard difference formula, but with different h values. And you will see this is a smallest one. And then if you go down here, and then the h size, the size of the h is becoming bigger and bigger. So this is the 0.001, and then this is 0.002, and then here, but here at the end you have 0.1. And this is the column for the approximations value of the derivative at the 0.9. And this is not very important. Let's just take a look at the errors. So we calculate the error by the approximations minus that true value, and then we get the errors. So let's see, you will see the number. This is the biggest one. We just look at the absolute value of the error. So it's bigger and then getting smaller, but here's another point here. It's not just getting smaller and smaller, and then but it happens to getting bigger again. Do you see the magic here? We keep. So let's say, okay, we are decreasing the h size. So if we decrease the h size, and then, okay, this is the big error. So big error, and then decreasing. Oh, it's increasing again, the error. So it doesn't make sense if you keep decreasing the h size. You say, let's decrease the h size, and then we get a better solution, a better approximation, but you can see the total errors has 2 parts, and then we need to do some compromise there. So now let's use the things we have already learned to calculate that optimal size. So let's take a look at the P table first. What do you think? Where is the optimal edge? The range, where is the optimal edge? It could be, so it's just decreasing, right? Decreasing, and then it's the same, and then but increasing again, right? So the line here is just going down, and then it's horizontal, and then going up again. So the optimal edge, it could happen in between this interval. And which means that the optimal edge, it could be between 0.005 and 0.05. And let's calculate that approximate optimal edge by the formula given by here. I'm just copying them, these things. This is the formula we get from the calculation. I just give the calculating the critical point there, but you can do your work after the class. So this is the optimal edge, and I'm going to get to this. But if you take a look at here, we are keeping only 5 digits after the decimal points, and which means that the error of the rounding could be smaller than 10 to the -6 and then times 5. And that is just 1/2 of the 5-digit points here. And then the epsilon should be the 1/2 and times the 10 -6. So here, let's say, what is the fx0? So f function f function is a sine function. And we calculate this 3 and then sine and then 0.9. And then the epsilon, because we keep the 5 digits after the point, and then the epsilon is just the 5 times the negative 10 to the negative 6. Because the error is smaller than this one. The rounding off error could be smaller than this one. Any question for this one? Let's keep going. And then that is 5 times the 5 times 10 to the negative 6. And what is the third derivative divided infinity norm? The third derivative, so what is the first derivative of the sine? The first derivative is just the cosine x. And the second derivative is just negative sine x. And then the third derivative is just the negative cosine x. So the negative cosine x, and I'm going to take the negative cosine x, and then taking the maximum among the interval. So we are considering the h values. So we are going to consider the maximum h value is the 0.1, right? So I am going to take the maximum number in between the 0.8 and 1. You know why I'm doing the same thing? Yeah. I'm going to get the maximum from the 0.9. So x is between the 0.9 and then this is the x0 point. And then subtract the biggest step size and then 0.9 and then plus the biggest h size here. So I'm going to take the maximum and then this maximum should be the cosine 0.8. Does it make sense? Okay, so this is the cosine 0.8 here. And then taking the 1/3. And using the computer or calculator, I got this value. It could be approximately equals to, I have some value here, and I prepared this beforehand. So I'm going to copy and paste, doing some copy and paste here. I calculate these numbers from the calculator, and then this is the utmost h size. And let's double check this. This is just the approximate optimal size, and then this number is lying in between here. And this agree with the numerical examples here, the numerical tables here. It's in between the 0.005 and then 0.05, and then but the actual value, this is just approximate the approximate optimal value here. And then this number is lying in between these two h size. Any questions here?
The machine position, how did you get that?
How do I get the optimal size?
The machine position, I guess.
Epsilon. Okay, good. The epsilon here, but this is like different from the binary format, and then but here the machine precisions because this is the rounding off here, right? And then so maybe the actual value for this one. So let's take a look at this one. This number sine x, right? And then it could be sine 0.1736 and then blah 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 here after it, right? And then it's using the rounding off and rounding down here to get the approximate value 71736, right? And because how do we do the rounding off for the decimal 10 base number? It's based on the digits here, and then if this digits is smaller than 5, and then we would drop it off, right? And then if it's bigger than 5, and then we would add 1 to the previous value, the previous places, right? So the error here should be smaller than. So this is just the error, and then 0.000, and then 0 here. And then this one is less than the 5, and then times the 10.6. And then the 10.6 is because this is the 10.6 point, 10-6. And then, but this one, it should be less than 5. The error between these two.
In the previous talk, you mentioned that there's a computer error in the computation of 10 to the power of 6. I don't find it on the board, so I don't quite get the point. Why is the error?
Oh, this line?
Yeah, the board.
On board, this one?
Yeah, so why is the error on that?
This one? Yeah. So, I just say, this is the machine precisions, right? Let's say this is a precision, machine precision 10 to the -6. And then from the analysis, and then we got this total error is a constant times the epsilon to the 2/3. So which means that if we get the total error for the finite difference formula approximations in the computer, we have the machine precisions. This is the epsilon. This is the epsilon. And then from the analysis, we got the total error. The total error, it should be approximately this magnitude. 10 to the -6, this is the epsilon, and then 2/3. And then we got the, if you calculate this, -6 times the 2, and then divided by 3, and then that should be -4. And this means that we cannot achieve the machine precisions. You can, so class is over. If you have more questions, you can come over here. And we would have homework 2 tomorrow. Homework 2 tomorrow.
So I have a question. So I just want to like piece it all together. So I understand this epsilon portion where it makes sense that like if we stop down or we start rounding there to then the largest
Error could be just 5 times 10 to the -6. Yeah.
What is this total error?
Total error, it means that the total error, it means that so because we are going to use the rounding off error value to replace the true value, right?
Yeah.
When we do
that's this
the
thing,
finite difference, right?
Yeah.
And then this is just a rounding off error. And then
this RH, right?
yeah, RH is a rounding out error. And then let's go back to the this part. So because we are using the rounding off error, rounding off values to calculate the derivative, right? And then not the true value.
Yep.
So we have 2 parts of the error. And then the total error in the approximations of the derivative.
So that's the ET.
Yes, that's the ET. And then there's 1 part from the finite difference formula, and then there's 1 part from the round off error. The
Okay.
round off error is coming from the rounding off for the data. And then the error, the first part, the truncation part, is from the finite difference formula. Because when we do the finite difference formula, do you remember what we did here? When we do the finite difference formula, we are truncating something. So let's see. So when we go back to here, we have the truncations for the interpolations, right?
Yeah.
And then that is why we have the truncations error for that finite difference formula part.
Okay.
So it contains 2 parts, the total error.
Okay.
If
yeah.
you use the finite difference formula in the computer to approximate the derivative, and then we have 2 parts error.
Got it. Okay. And then what's up with like the machine error? Is that the same thing as the epsilon?
Yes, that is the machine precisions.
Machine
Is
precision.
the epsilon is just the notation for the machine precisions.
So isn't it always going to be the case that like the total error would be less than the machine error?
Yes.
Okay.
Yes, from the analysis, it is not less than. It's always bigger than the machine precisions.
Always bigger than, yeah.
Yeah.
Okay.
But the number is smaller. This one, the number, the 4 is smaller than 6.
But it's still bigger.
Yeah,
Okay.
in the magnitude, it's bigger.
Yeah. Okay. Got it.
Okay.
Thank you.
So like the machine position is like the best position you can.
Yeah, yeah.
And because of there's like round off error, so you can achieve
Yeah.
too hot.
Oh, can I take the picture of the
Yeah.
example slide?
I will post it on the cameras.
Yeah. Yeah. I think
Last
you-
class you said that we might have to derive the formulas for like the standard
I took
difference quotient stuff. But in 104A, the way we calculated it was through like Taylor's theorem.
Yeah,
Would this be also another?
there are two different ways to, a lot of ways actually. We can use different interpretations of polynomials to get it. So here we use the interpretations polynomial, but you can also use the Taylor expansions to get their formula.
Either one would be good on the test.
Yeah.
Okay.
Yeah.
Question to you on the homework. It says to prove that you get 1.0 times 10 to the negative 1. But like I was doing like the same steps, and I feel like my question is the same because when you expand that, you should get this. And so shouldn't you get 1.0 times 10 to the negative 2, like in the demo?
Okay, let me see. I haven't taken a look at the homework, so for details. So now show all your word by step and then the representations for.
Yeah, just look it up.
Okay. So here we have
Yeah.
X,
Was it one of them like you transfer it from
Y.
base 10 to base 2?
It's converting it to,
Okay, and what's that? What's your questions?
So my question is because when you expand that, you get this form. Right? So when I did it, I got the same 1.0 times 10 to the negative 2.
Let me see. So it should be 0.25. And then, let me see. It should be rounding off. How many digits do we keep? We keep, I think we just keep like, do we specify how many digits we want to hit? We only keep one digit, decimal digit.
Okay, so when we do the
Yeah,
so when we do this, do we do 6.3 times 10 to the negative 0?
so here you have x squared, right? And then what's the x value?
The x value is 2.5 times 10 to the 0.
Yeah. So you here is
Yeah.
about 2.5 and then to the square, and then rounding off to the one decimal.
So we do 6.3 times 10 to the 0?
Yeah.
Okay.
And then that is 6.3,
Okay,
right? Okay.
got it.
We only keep.
One digit.
decimal.
There's the statements in the very beginning.
Okay, got it. Sounds good. Thank you.
And then I'm gonna be gone Friday. Are you gonna record?
Yes, I would record the video and then post the videos to the cameras if I remember